Good morning, everybody, and thanks for inviting me here. I'll try to present, unfortunately, online because I could not come in person by physical reason. Now our presentation will be about maybe most complex and most ubiquitous phenomenon. It's just classical hydrodynamic turbulence. It is complex in the sense that there are many different scales, many different types of motion. You can see there is the example of the Baltic Sea turbulence, which made visual due to the blooming of phytoplankton here. You see all this complexity with many vortices, many scales, and etc. You can find a lot of such pictures on the internet. What is our problem here? What we are going to discuss? It is the following. It's well known that the small scale or mesoscale turbulence in the ocean exists almost everywhere in the ocean, even at different depths, up to big ones. And it can live long sometimes in the form of spots, sometimes in layers, different kinds of structures. And the question is why? Why do they live so long? Because it's known that turbulence itself is dissipating due to the transforming of larger scales to the small viscous scales. So in this case, we need to consider also the shear flow due to the currents or maybe internal waves or something else. And in this case, the turbulence existence is a hint on the balance between velocity shear, du dz, and density stratification, which is characterized by Brent value of buoyancy frequency, which is proportional to the gradient, vertical gradient of velocity. So in fact, we need the Richardson number, which is a ratio of these two values, which is shown here in red. And what should be this Richardson to sustain the turbulence? The early and up to now, the main maybe theory which is used is the theory of John Miles, who linearized the equations of shear flow in the stratified density stratification, and obtained that if this number Richardson is smaller than 1/4, it can be unstable. When it's unstable, it can grow and break and create turbulence. But much of turbulent areas in the ocean exists for much larger Richardson number. So the next approach is the average semi-empirical theory, K epsilon, they call it often. It's just a Reynolds or Kolmogorov-Reynolds model for turbulence. And from this, from the usual approach here, we obtain the threshold Richardson should be less than 1. It's already better, but it's not enough, because in many cases, Richardson is more than 1, and still the turbulence leaves. So there are some references that I will show you some example here. So now it's our approach, what we suggest. We modified we modified this K epsilon theory as long as in 87 with Troitsky, is taken into account the potential energy of turbulence, which is due to the mixing of density at the layer in the presence of the average stratification, which is also needs some work. And it was shown that due to the transformation between kinetic and potential energies, this threshold, any threshold, just disappears. So in principle, turbulence can exist and not dump can be supported at any reaches of number, even very big. So now we based on this, and show a few examples of real ocean observations and apply the theory to Z. Okay, but before maybe a couple of slides about the theory, just to remind it. It was started from the kinetic approach, from the probability or distribution of velocity V, turbulent velocity V and density, not only turbulent, all the velocity and density here, and we substituted it in the classical hydrodynamic Navier-Stokes equations. Yeah, I will not show it here. It's too very well known. And first we obtain the expressions from the average the momentum flux, like here, and mass flux, which is here. This is average flux for turbulent pulsations. And the new element is this non-gradient term, which is in red, and which is proportional to the gravity acceleration, to G, and proportional of the average the square of density fluctuation. By the way, this beta is a bit more complex term, which is also proportional to the rho prime square here. And so these terms results, all these results in this total system for average velocity, density. K is the kinetic energy average of turbulence, and rho prime square is connected with the potential energy with it down here, which is proportional to rho prime square, so it's the same. In what follows, we will not consider all this stuff, but only these two equations here, which is in red for K and rho prime or P. And moreover, for the beginning, we consider average shear flow U given, and what else is here? So the density average term also given, and for the beginning we did neglect diffusion like this, terms with ddx. But in this case, because without diffusion we don't have ddx, we have just local in every point equations for K and P for two energies. Here, n square is a given Brandtweiser frequency, and R is some anisotropic parameter with related to beta, which I showed before, and here is 0.5. L is the external scale of turbulence. Here we put it 30 centimeters, 33, and C and D are just coefficients for dissipative terms, which are here, of course. Dissipation is here, and here they are taken 0.09 empirical stuff. And the final result will be dissipation rate of kinetic energy, which is here in red, because it's typically measured value of in the many oceanographic experiments, especially near the surface. Okay, so we start with these equations, and before considering the real equation, you see that both energies go to constants here, to equilibriums, and these equilibriums are shown for some parameters and for two Richardson numbers, 0.5 and 5. So it's pretty much more than 1. Left 0.5, right 1. You see in both cases they go to the constants, non-zero, they don't dump. And moreover, the values of these asymptotics are comparable here. Actually, for potential energy is even more for big Richardson because interaction with kinetic energy is stronger, but kinetic energy is it's slightly smaller than this. So this is just a simple equations for stationary values of here from which we will start. In here you see there is a square of shear velocity. This is a turbulence scale, and F is a function of Richardson number, which is down here. And what is important for the future is that in all the range of Richardson numbers from 0 to infinity, it only changes from 1.2 to 2. So the main parameter here actually shear square, the velocity shear square here. So now, after we show this just example, we show you some ocean turbulence results. We start with the paper by Porian and others. The detailed references are in the end, and they give. It's not often that we have all we need. They give the shear here. Depth dependence of the shear. Here is pressure, but pressure in decabars, actually decibars, and when the density of the ocean is close to the ocean, this is almost the same as the meters here. So we even do not need to recalculate. Maybe it's a difference of less than 1%. And so you have the shear, you have the pressure, sorry, you have the density here, n squared more exactly, not density, but the gradient of density here. And they measure this dissipation rate here. And it is for three cruises, 3 places in different areas of the ocean. This is for North Atlantic, this is Iceland, near Iceland, and this is in Southern Ocean, so it's almost the antipode of these two. So what could we do? We could take these 2 lower rows as given, and then calculate this upper row and try to compare with their measurement result. Also, pay attention to the big dispersion, of individual measurement, which are in gray here. There are sometimes it's ordered, not at least another value, So we start from the average red. Then we will try to do something about this too. Okay, then first of all, we plotted the Richardson number for this data. And as you see, for all three cruises, all three places, this is practically everywhere, always more than one, two and more, and up to even 20, 10, 20, 25 here. So now we should apply it and show that it still may exist like we see from the experiment. First, we took the one cruise. We consider all cruises, and this is the time variation for different depths here, between different depths. And you see all them grow from some initial, we take it very small, and then it goes, everything go to the constant. Here's a constant, there's a constant, and so on. And this is the, then we will work with this asymptotic constant because we know nothing from the experiment about how long it takes this. Usually it's, you see that it's second, so a few hours maybe, but we probably have the pictures which longer than a few hours. So this is asymptotic energy versus depth are here. It's horizontal, not vertical, so depth is here. So this kinetic and potential energies, and this calculated dissipation rate in these areas. Blue the shear and green the field data which was there in red. There you see there is some difference, but only maybe a half order. This is also not zero. It's logarithmic scale here, so maybe 3 times. So taking into account the dispersion I showed you, which is about the order, and order, I think it's pretty good here. This is the same asymptotic from the other cruises. Here, this is the energy and potential and kinetic energy here. And here, the dissipation rate. What else here? Yes, this is a kinetic energy for another cruise. So it's now we have all three. And this is also blue theory green experiment. And also typically it's almost the same here. It's also very close here. And the only thing maybe here we have more than order in this area only. But it is the case when the dispersion is especially, this is this kind, so it's especially big. So it's not surprising. Okay, now the next question is we neglected the diffusion. Now we'll try to add the diffusion. We use some expressions for the fluxes of this energy in this case we need, and calculated this equation, partial derivatives, of course, now 1D, and calculated it for asymptotics too, and compared diffusion case and a local before Z. Blue is local, red is diffusion, is full with diffusion. You see that practically the same for this, for all cruises. Actually, no difference. Here it's even not noticeable. Difference may be a little here. Okay, so diffusion is indeed very small in this, at this time scales, this vertical scales here. Okay, the last about this work is it's about the scattering of data. You see, for example, for 306, scattering is shown here from the experiment here, and this is our calculation in the worst case. Worst we mean that we take the for example, maximum the maximum difference for velocity, it will be a minimum difference for density. There is no such a plot, just no place here. You see, and so it's worse than here because we did not only this, but we also did density. We don't know which one correspond to which one in density. So it should be worse than here. But it is maybe a little worse somewhere, but we see that our plot is indeed within this area. So it's also not too bad. Okay, this is about this work. Now, if I have some time, it's about another paper from Mo, Farmer, and others. It's about turbulence in the strong internal way, soliton, strongly non-linear soliton here. You see this one of the many solitons they have there, and the left is this echo sounder, and red is the big, strong scattering. Here, the sonar is on the ship, so it's on the top. We have also, of course, the strong scattering from near surface because there is a lot of turbulence due to the breaking of surface waves, but also here, on the picnic line, thermal line here, where is a strong gradient of density. And they also measured the dissipation rate, and the same. Here, we also have some data about this, where is the strongest dissipation rate in the same area. So the strongest where turbulence is strongest. So we started from very rough model. We approximated this displacement here, and then found the horizontal velocity above and below this. This is horizontal velocity over this and here, and this is below here. And naturally is negative here, as it was in the paper too, by the way. And then we calculated kinetic and potential energies, and from there the dissipation rate, and plotted it in the same contour plot. As here we see that it is something like that, not too bad, not too much worse than here. Okay, but then we even tried to do more. We took the data of the vertical distribution of velocity here from the same D306. And this is just a table of some plots, discrete, and this is the same for density. Sigma is very well taken in the oceanography, is just delta rho over rho over 1000. So it's just about 26 maximum. Of course, it grows down, so it's a stable stuff. Okay, now we approximated it with some polynomials. This is approximation for the velocity and for density here. From that, it is a shear square which is needed, and this is the n square here, what we need to use. You see there's some maximum for shear square. It's about this depth, where the maximum was here. And n square is also maximum somewhere close to this. We don't consider much the upper layer. I said that it is probably due to the breaking. Okay, now then we calculate the Richardson number. You see it's more than one almost everywhere. Here, even more here than 7. And this is the kinetic and potential energies. And this is dissipation rate here, which we plotted here. And as you see, we compared it with that. With some plot, with this, with a plot of, they don't have such plots. We need to recalculate this to, so it's one point where the displacement is maximum or near maximum, exactly. And it is not too very far from experiment. This is about 10 to minus 5. It's a bit more than, maybe at least half order more than the in that data, which we can see at least. Then we took the soliton and plotted this for along the soliton. So we obtained this epsilon, the dissipation rate everywhere here, which is more or less like this. So it is maybe not as good as before, so we still work with it, but still maybe it's the first time when it was possible to predict the turbulence for internal waves here. Okay, it's almost all. So the conclusions that the complexity of turbulence is enhanced by the shear flow density stratification. So it's due to the source and sink of turbulent energy, plus of course dissipation. And they are typically shear stability or wave breaking are typical sources turbulence, and it may be maintained and enhanced by stable currents and non-breaking internal waves. So maybe they were created by instability, but they would die much shorter in the tails. So we added the potential energy here, potential energy, and in this case, we show that it can exist at any Richardson number, and we confirmed it with a comparison with the real experimental data. And I think for now, is maybe only a mechanism, at least more natural, to explain these facts. Okay, so if you need, I can give you this all references. Thank you very much.